So you guys at home, you've got a packet that's posted in Schoology. It's notes for today, homework for today, notes for tomorrow, homework for tomorrow. So it's kind of all bundled up together. Let's just do a quick little review up here at the top. The integral of f of x dx from a to b. So yes, that means area under the curve, but it also means antiderivative at b minus antiderivative at a. All right, the first two problems it's the same problem. We're just going to go about it two different ways. So given that the y dx is equal to this with the initial condition, remember we use that to find c, find y of 3. All right, method 1, integrate, use the initial condition to find c, write the particular solution, that means using c, and then use that to find y of 3. So the integral of 3x squared plus 4x minus 5 would be x cubed plus 2x squared minus 5x plus c, using antiderivative rules. And then we know that y of 2 equals negative 1. So if I plug in 2, I can figure out what c is. Let's see, 4 plus, oh, that was cubed, sorry. So 8 plus 8 minus 10 plus c. 16 minus 10 is 6. If I move that to the other side, I get negative 7. So c is negative 7. So now we know what the particular solution is. And now we can find y of 3. We'll plug in 3. 3 cubed plus 2 times 3 squared minus 5 times 3 minus 7. And by the way, that'd be a safe stop. Like we could just leave that there as our answer. I want to be able to compare it to what we're going to do next. So yes, we could leave that as a safe stop. But if we did the math, we get 23. So we knew you could do that even before we did fundamental theorem of calculus. That could have been a problem on the last test. Integrate, use an initial condition, and then use that to find another point, y of 3. Now, there's another way to go about this, and that is, so forget all that we just did. The integral from a to b of f prime equals f of b minus f of a. Like this is sort of one of the matching ones, right? The integral of f prime gets you right back to f. The antiderivative of the derivative gets you back to the original. So the antiderivative, now we know that y of 2 equals negative 1, and we're trying to find y of 3. So we should probably use those as our limits. So we'll go from 2 to 3. And we'll integrate 3x squared plus 4x minus 5. And even before we integrate, with those limits up there, we know this will equal y of 3 minus y of 2. Does that make sense so far? Yes? No? Okay. Well, we can evaluate this, we can do that. Y of 3 is what we're looking for. And y of 2 we know, that's just 1. So we can figure out what y of 3 is by finding these other two pieces. So let's integrate over here. We just did this integration. X cubed plus 2x squared minus 5x. And I don't need the plus c this time because I have limits to worry about. So I'm just going to go from 2 to 3. So if I plug in 3, that would be 27 plus 2 times 9 minus 5 times 3 minus, plug in 2, 8 plus 8 minus 10 equals y of 3 is what we're looking for. Y of 2 is 1. So this isn't a safe stop because I don't have y of 3 by itself yet, but as soon as I move 1 to the other side, I could safe stop this thing. 27 plus 18 minus 15 minus 16 minus 10 is 6. I'm just going to move that minus 1 to the other side, plus 1. And I could safe stop that right there. But if I wanted to compare it to type 1, what do you know? It's also 23. So in method 1, we explicitly found C and used that to find the missing piece. In method 2, we sort of short-circuited around C because we could use the fundamental theorem of calculus. This is tricky, but we're going to get practice on method number 2 here, because it's a little bit quicker when you get the hang of it. Plus, you can do method 2 with a graphing calculator. Sometimes there is no antiderivative, so we have to use method 2. So you can't even undo sine of x squared, right? Because the antiderivative of sine would be negative cosine, but that x squared, the chain rule would mess stuff up. So I don't know yet how to antiderivative sine of x squared. So let's just see what we can write to figure this out. We want to integrate sine of x squared, even though we don't know how. What should our limits be? What x value should we use? Well, look what we have and what we're looking for. So let's go 1 to 2. Because the integral, like if f prime is sine, then the integral of the derivative would be back to f of 2 minus f of 1. Find f of 1. So if I move some things around, if I move f of 1 to the left and that integral to the right, we get f of 2 minus integral from 1 to 2 sine of x squared dx. But I know f of 2, that's negative 5. This I can do in the calculator. So this is the fun part of what the calculator can do. I can find mine to use here. All right, let's see if I can remember where this goes. Math 9, function integration. And if you have an updated operating system, it'll look like that. If yours just says, anybody's just say fn int open parentheses, good. You can still do it that way. It's just kind of a pain. Here it looks like it's supposed to look. So from 1 to 2, Okay, be careful. We're taking the sine of x squared. We're not squaring the sine of x. And so even though we can't do that like symbolically, even though I don't know what the antiderivative of sine of x squared is, the calculator basically numerically can graph that and find the area underneath it. That doesn't look right because I'm in degrees. So be in radians. And we just want -5 minus answer. That way we don't mess up any decimals and let the calculator handle all of that. So f of 1 is -5.495. That's a concept-heavy problem, not a computation-heavy problem, right? We didn't do much of anything other than type stuff in the calculator. But there's a lot going on, and we had to know what to type in the calculator. Let's keep going on this. More practice problems coming. The graph of f prime. Okay, here we go again with being careful with what we're looking at. That's the graph of f prime. It consists of two line segments and a semicircle as shown on the right. Given that f of -2 equals 5, find f of 0. Well, if I want to find some f stuff, I need to integrate f prime. Let me write that up at the top again. The integral of f prime. Yeah, the integral of f prime. The antiderivative of the derivative gets me back to the function. Say it that way. Use the right words and it's easier. The integral of f prime is f, but the antiderivative of the derivative gets you right back to where you started. So if we want to find f of 0, and we know f of -2, then we should probably write the integral from, let's be careful. Which one of those is the smaller number? -2. From -2 to 0 of f prime of x dx equals f of 0 minus f of -2. Top one minus the bottom one. So the integral of f prime from -2 to 0, well, I can get that from area under the curve. Let's see, 2 times 4 is 8, divided by 2 is 4. So that area is 4. So 4 equals f of 0 is what we're looking for. F of -2 is 5. So that means f of 0 should be 9. Questions on that one? All right, for B, almost the same thing, except now we want to find f of 2. So we're not really concerned with 0 anymore. We're worried about -2 and 2. So we want to go integral from -2 to 2. And again, top one minus bottom one. So similar to the last one, why don't you see if you can take it from there? F of 2 is 13. Did you get that? Again, real similar to the previous one. All right, try C completely on your own. See if you can take it start to finish. All right, so 6 and negative 2. Negative 2 to 6. F of 6 minus f of negative 2. So same process. Area. Let's see. That radius is 2 pi r squared over 2. So that'd be 4 pi over 2. That'd be 2 pi. But it's negative. So that's the main trick on that one is, wait a minute, it's underneath. So it's probably wise to label it's negative 2 pi because we're underneath. So to get from negative 2 to 6, that area would be 8 minus 2 pi. F of 6 we don't know. F of negative 2 is 5. So now we just move the 5 over and we get 13 minus 2 pi. But the big trick, I don't know, thing to be careful about on that one is that 2 pi was underneath, so it's negative. Next example is pretty similar. I don't know if this is clear. That area is 4. That area is 9. That area is 2. Now, before we even get started, same issue. What am I going to be careful about here? That's negative 9. I'm probably going to just label that negative 9 from the get-go rather than having to try to remember to, don't forget it's negative. Just label it negative 9. The area isn't negative 9, but the integral is negative 9, and this is just notes to yourself to help, so I would label it negative 9. All right, f of 3 is 5. Again, this is the graph of f prime, and so if we integrate f prime from a to b, we get f of b minus f of a. That's probably how we want to remember that. Like you can memorize the other forms of it and say f of a is, I'm going to mess this up. No, let's do it this way. F of a plus the integral from a to b gets you f of b. To me, I don't remember it that way. I just always write it this way and then move things around as needed. Otherwise, you're memorizing 3 different things that are all kind of the same thing. So you get this, and then you can adjust it as needed for whatever the problem is. So find f of 0. Well, so my key x values here are 0 and 3. So I probably want to integrate from 0 to 3. Area under the curve from 0 to 3, which that's nice. They just gave me the area under the curve from 0 to 3. I'm going to finish writing this statement before I start filling things in. That would be f of 3 minus f of 0, because the antiderivative of the derivative gets me back to the function. So really this example is just like the previous one. Arguably it's easier because they just tell you what the area is. You don't even have to know triangles and circles. So 0 to 3 is 4. F of 3 is 5 because they gave us that. F of 0. Well, I guess algebraically this is a little bit different than the previous one because the f of 0 is in a different spot, but this is just moving things around. So I'll add f of 0 to the other side, subtract 4, and get 1. Part B, from I don't know that I want to go 0 to 7. I guess I could go 0 to 7 since I know f of 0, but I probably should use original information, so let's go 3 to 7. Right? Does that make sense? Like you could use 0 because we know what f of 0 is now, but in case we mess that up, let's use original information here. So from 3 to 7, but only 3 to 7, not anything else. 3 to 7 is negative 9. F of 7 is what we're looking for. F of 3 is 5. So f of 7 is -4, I think. Once again, you try part C, and then we'll compare notes and see where we look, how we look. So let's see. Integral from 3 to 9, be f of 9 minus f of 3. Again, I want to keep using 3 because that's the one I know. Area from 3 to 9, so put them together, well, include the negative, put them together, is -7. So if I add 5 to both sides, I get -2. Sketch the graph of f. Well, normally I don't think I would like that very much, but I've got 5 values for f, so I'll plug those in, plot those, and see how things look. So f of 3 is 5. That's the biggest y value I've got, so f of 3 is 5. F of 0 is 1. F of 7 is -4. And it's a sketch, so we don't have to be, dead on perfect here. And f of 9 is -2. Well, we hadn't talked about this in a while, but at x equals 3, f prime is changing from positive to negative. So what does that mean is going on at f? F has a max, because it changes from positive. F prime changes from positive to negative, so f has a max at 3. Well, that fits exactly what our picture shows. The opposite thing happens at 7. There's a minimum. So let's just kind of sketch in with what we've got here. It just says sketch, so it doesn't have to be perfect. All right, last one, then we'll maybe do one or two off the homework. A pizza with a pizza with temperature of 95 is put into a 25 degrees C room when T equals 0. The pizza's temperature is decreasing at a rate of this thing. Estimate the pizza's temperature when T equals 5. So let's do a little table here with stuff that we know. When pizza with temperature of 95. Okay, so that'd be at time 0. When we first start this experiment, it's 95 degrees. We want to know what's happened, or what the temperature is at 5 minutes. And they give us this thing. And they say the temperature is decreasing at a rate. So you know what? Instead of calling that R, it's fine to call it R, but that's the rate of the temperature change. So I think I would rather call that T prime, the temperature change. And because it's decreasing, tried to sneak this past us, I'm going to put a negative on that. So if I can integrate T prime, I'll be back to T, which is what I want. And I've got some values here. So let's integrate T prime from 0 to 5, because that's the points we've got. So that would be the temperature at 5 minus the temperature at 0. Well, the temperature at 0 we know. This thing over here as ugly as it is, can be done in the calculator. So this is definitely a calculator problem because I am not going to antiderivative that thing. Although I guess we could. We know the rule, but it's a calculator problem. So use the calculator. Math 9 will be your best friend for this unit. 0 to 5, negative 6, e to the negative 0.1x. And again, your calculator doesn't care what letters you use. So this is in T, but we're in X's in the calculator. It doesn't matter. You could actually use T in both of those, but probably safer to use X. So that represents how much the temperature changed between 0 and 5. It's negative, but that makes sense because the temperature is going down. So T5 equals 95 minus 23.608, whatever the calculator says. So 71.392. 3 decimals, always 3 decimals. So another problem, when you get to use the calculator, it's a blessing and a curse, right? It's the blessing because the computations are easy. It's a curse because usually the concept is hard, and they're giving you the calculator to kind of make up for the fact that the concept is hard. That's sort of what's going on in that example. All right, the homework is the next page, the next worksheet, just the next worksheet, not the one after that. And 1 through 3 should be no calculator, and then after that, with calculator. So let's do, and there are answers on the back. This is true. This is true. Let's do number, 7. Let's do number 8, actually. Make sure we know the words here. Number 8. A particle moves along a line so that any time its velocity is given by that thing, and we want to know stuff about its position. Remember that velocity is the derivative of position. So that means the integral of velocity, if we integrated both sides, would give us position. So again, being able to work forward and backwards. Derivative of position gives us velocity. That means the antiderivative of velocity gives us position. So 0 and 3. Once you start to figure out what to look for, these aren't too bad. So if I integrate velocity, I'm not even going to plug it in there yet. If I integrate velocity from 0 to 3, if I antiderivative velocity, I get position. So this would be s of 3 minus s of 0. But this is a calculator thing now, right? I can integrate that in the calculator. And I know what s of 0 is, so this is just s of 3 equals s of 0 plus the integral, whatever that is. But again, it's a calculator problem. So once you get it set up, the fraction bar is in there too. Remember that if you like it. The alpha F1. There's enough parentheses to worry about. So there's my integral, 1.15. Careful, that's not the answer. That's how much it's changed from 0 to 3. So if I add 5 to that, I get my answer. 6.151. That's easy when I do it, isn't it? truth. Answers are on the back. Let's see if we got it right. See if I got it right. Got it.
6.249.
Let's say, what was your integral? All right, so again, 1 through 3, try without calculator, and try the rest with calculator. Answers are on the back. Answers of the odd ones are posted in Schoology with the work shown. So if you get stuck somewhere, you can hopefully see what happened.